Hello everyone. So let's read over this problem. A ball with a radius of 6 inches is tangent to the wall and the floor in my house. Given that the wall is perpendicular to the floor, what is the radius of the largest ball I can slide into the space between the ball and the corner where the wall meets the floor? Alright, this is kind of wordy, so let's just start. We know there's a wall on the floor, so let's start simply by making our wall. And then, let's see, perpendicular line, which will represent the floor. So, I don't think we need to even label these points. Not really, nah. Alright, so we have the wall on the floor, and we have some sort of ball tangent to the wall on the floor, which means that this ball is touching the floor at one point, and it's going to touch the wall at one point. That's what the tangent means. So, ball implies sphere. Now, spheres are very hard to kind of draw in 3D. My recommendation is whenever you have a problem with a sphere, just try to represent it as a circle. Take a cross section of that sphere and represent it with a circle. So, let's make a circle. Take a compass tool, select segment or 2 points for the radius, whatever. Alright, can I make this not as big or what? Actually this could be fine. Hold on, let's, yeah, so, alright. There, we're going to have our, this is going to be our large ball with the radius of 6 inches. Okay, so how can we approach this problem? Well, we know that tangency implies right angles. So, for example, if I connect the tangent point here with the center, that forms a right angle. And if I make one here at this tangent point, we got another right angle, which means we have made a square because we have two of the sides being the radii, which is going to imply all the sides are the same. Okay, that's fine, but what else do I need to solve this problem? Well, I'm trying to find whatever ball is going to fit in this blank space over here. So, this theoretical ball is going to take up the maximum amount of space. So how can I figure out what that would be? Well, if we have a square, we can make some triangles out of that by connecting the diagonal. Now, we have this distance from C, and let me start labeling these points, C to E, which would be the length of the radius, which is 6 inches. Now, if I were to sort of think of maximizing my space between E and this point here, B, because somewhere in here is the center of my new circle. If I want to maximize the space, maybe think of what the midpoint is. So if we locate the midpoint between B and E, this is going to be this point F. And now if I make a circle with this center at the midpoint, that is the maximum distance I can have between B and E. So let's make that circle. So we have a circle with a center at F, and we want that to fill up as much space. Now, it doesn't look like it's taking up as much space as we like, so what we could just do is instead move the center. Can I move that? No, I can't. Okay, let's trash that then. Alright, so let's just imagine this theoretical circle where there's this center and a radius that we can sort of maximize. So it's going to take a little bit of work to kind of get exactly right, but it's going to look something like this. And this is me just being a perfectionist, really. Something like that. Okay. And I'll even put G here or something. Alright. Now, we have this new circle. Now, using the visualization, can we find out what exactly is going to be the radius of this ball, this theoretical ball that's going to fit in this space here? So let's label some of the stuff we know. Well, we know that E to C is the radius, which is 6, and this radius must be the same as CD. And since this value here is also a radius, I guess we could just call this point A. So CA is also the radius. So we have 6, and we form this square, so we know that BD is also 6. Well, now if we examine the triangle CDB, we notice that, again, tangent lines imply right angles, so this is going to form a right angle here. Whenever you see tangent lines, think right angles. Right angles imply right triangles. Now, triangle CDB has two sides that are the same, which means that it is a 45, 45, 90 triangle, which implies that the length of the entire hypotenuse, which would be CB, is the length of the side 6 times the square root of 2. Now my goal is to find the radius of this circle, the smaller circle. What is this radius going to be? Now if I rearrange a little bit like this, that radius, I could use either FE or FG to figure out what that radius would be. So I'm going to note that these two lengths are the same, and I'm going to call it like R, because we're trying to find the radius R. Now, this means that we have two lengths of R here. Now, if I could find out what EB is, or any of these values, then that might help me find out what R is. Well, I know the total line CB is 6 root 2. That means that the smaller portion, EB, is equal to 6 root 2, the large hypotenuse, minus EC, which has a length of 6. So that must be what the length of EB is. It's the length of BC minus the length of EC. Now, how can we continue from here? Well, I want to find out what the radius is. Well, let's say in order to find out that value, I would need to figure out, well, we could try to figure out BF, for instance, because the problem is we have this unknown length for BG. That's the issue we're running into. So how can we express the length of BF? Well, BF would simply be the length of EB, so which we know is 6 root 2 minus 6, but BF is the length of BE minus one of the radii, FE. It's BE minus FE, so we're going to minus the radius from that. Alright, so we have all these expressions, but what can we possibly do from here? Well, think of the same tactic we just used. We created a triangle using the lengths of the radii. So let's see if we can do the same thing. Let's create some more radii in our circles, because we have another circle that's tangent to two of these positions. And what do you know? We get more triangle lengths that we could work with. So for example, FH is a radius, and BH would have the same length as a radius, because by the construction, IFHB is going to be a square, which implies that we could, well, we know that this is R and this is R. So if BF is the hypotenuse of the triangle BFH, where there's a right angle here because it's a tangent line, and BFH is a 45, 45, 90 triangle because the two sides are the same, FH and BH, which also implies that the hypotenuse, again, based on the same reasoning we used before, the hypotenuse is the length of the side times the square root of 2, and the length of the side is R, so it's R times the square root of 2. Well, now we can form an equality with these two equations. BF equals 6 root 2 minus 6 minus R. BF is also equal to R times square root of 2. So let's set them equal to each other. So 6 root 2 minus 6 minus R is equal to R root 2. Okay, well, I'm going to group the R's together, so I'm going to add R over here. So we have 6, and I'm going to also note that we have a 6 and a 6, so we can factor a 6 out. 6 times root 2 minus 1 equals R root 2 plus R. Now, going on, we can also factor out an R on the left-hand side here. So if R times square root of 2 plus 1 equals 6 times the square root of 2 minus 1. Well, that's interesting. We should be able to solve for R now. So divide both sides by the square root of 2 plus 1. Square root of 2 plus 1 So r is equal to, because these are now going to cancel out, well, this weird looking thing right there. Now, this is really something you're hopefully going to learn more about in Algebra 2. If you were really crazy, you might have learned about it in Algebra 1. You have to take something called a conjugate, where we're going to have our 6 times the square root of 2 minus 1 over the square root of 2 plus 1. And to rationalize the denominator, to get the square root out of the denominator, we're going to multiply by the conjugate, which would be the square root of 2 minus 1 over the square root of 2 minus 1. Now, why would I do that? Well, the logic is because when we multiply the denominators, they'll become a non-square rooted number, since the square root of 2 times the square root of 2 becomes a regular 2. Then we do square root of 2 times negative 1 plus 1 times square root of 2. That would cancel out. And then finally have 1 times negative 1, which is negative 1. And then we just multiply the top parts. So square root of 2 times the square root of 2. I'm going to leave the 6 out. Is just a regular 2. The square root of 2 times negative 1 is negative square root of 2. Minus, we have negative 1 times the square root of 2. Another negative square root of 2. And negative 1 times negative 1 is positive 1. I know this is a lot, but just try to keep yourself organized. Now we can reduce it. 2 minus 1 is just 1, so it cancels out the fraction. Anything over 1 is itself. We have 6 times, we have 2 plus 1, which is 3, minus, we have 2 square root of 2's that are negative, so 2 square root of 2. Alright, now finally we can multiply stuff out. 6 times 3 gives us 18. And 6 times negative 2 is negative 12. Keep the square root of 2. Oof. So, that is our final answer for the radius. I know it's a lot to follow. Just, if you need to pause and really keep track of what I'm doing, this is probably the most complicated type of geometry problem we're going to do. Hopefully you can see all the steps I'm doing and really understand how the process works. And if not, I would just recommend watch it, the video again, just slowly, one step at a time. Make sure you understand the logic of every step in the process.